Alright, welcome to our video on spectrophotometry and Beer's Law. So quick little flashback. Remember that when we talked about electrons jumping up and down, when they fall down, they give off photons of light. Well, in spectroscopy, we're going to do the opposite. So rather than seeing light coming off of matter, we're going to shine light at the matter, and it can be any type of light like electromagnetic radiation, radio waves, microwaves, infrared, ultraviolet, Roy G. Biv, etc. And basically we can use spectroscopy to determine concentrations of solutions. And in the college level or research level, you'll look at actually what kind of bonds are present in a molecule. That's why ways we can find what a molecule looks like. So again, electrons fall down like you can see up here, and when they fall down they give off these colors of light right there. Well, if you shine white light, Roy G. Biv, all the different types of light here at matter, those exact same slivers that were given off when electrons fall down, well, they'll actually absorb light from those areas, and that's why it's a black line. So the top one's what we call an emission spectrum. The bottom one's what we call an absorption spectrum, which colors of light are absorbed. So what is spectroscopy? It is the use of light or electromagnetic radiation to study matter. In spectroscopy, we use a spectrophotometer or a colorimeter. So what they both do is they are devices that are employed to measure the amount of light absorbed by a sample. What makes them different is that a spectrophotometer can, you take every frequency of light, visible light, Roy G. Biv, and when you shine that at light, you can see which of those colors are basically absorbed. And a colorimeter can't do all the colors. Colorimeters usually just do very specific wavelengths, usually a red one, usually a yellow, a green, and a blue. So if you look at the colorimeter you're seeing down here, that's what this is. There's only 4 different wavelengths that can actually be measured. So that's the difference between a spectrophotometer and colorimeter. But they both can measure how much light is absorbed by a sample. So here's how a spectrophotometer works. You want to take a few notes in there. So a spectrophotometer works by passing a beam of light through a sample, and you measure the intensity of the light reaching the detector. So if here's your light source, light will shine through, and it's going to go through an entrance slit, which basically kind of like gets rid of all the light. You don't want a ton of light coming through, you want a very small sliver, so it's a slit of light will go through. It will go through some kind of prism or grating, and we call it the monochromator. Basically it selects the color of light we want. So you don't want all of Roy G. Biv at times. You want to measure just certain colors for absorption. And once you get the color you want, only that color goes through. So in this case here we have red. And then basically the light will go through your sample and get measured by a detector. Now they're using the letter P here. I always use the letter I. I stands for intensity. And basically there's an initial intensity, so usually that's pretty big. And as the light goes through, some of the light gets absorbed, so your regular eye at the other side here, the intensity goes down, and basically when the intensity goes down, you can measure how much light was absorbed. So that's a spectrophotometer. A little bit more here. So a beam of light, remember, consists of a stream of photons, and it's represented by the purple balls in the simulation that we'll see in a little bit. When the photons encounter an analyte particle or molecule being studied, there's a chance that the analyte will absorb that photon, and the electrons in that molecule absorb it. The absorption will decrease the number of photons that will go through. So if here's your sample right here, and here's our detector, and here's where the light comes, as you go through your sample, the amount of particles going through will decrease. So if you have, let's just say 100 photons per second going through, the detector might only measure maybe 50 photons per second. That's because about 50 of the other photons were being absorbed. So it reduces the intensity. So, real quick question for you. What part of the molecule or atoms do you think is absorbing the photons? Go enter your answer. So you should have said the electrons. They're absorbing them. Oftentimes we need to also determine what is the right light to shine at your sample. So to determine the right type of light, and we're just going to work with visible light now, Roy G. Biv. Which type in Roy G. Biv? Red, orange, yellow, or green, blue, indigo, and violet. Which one should you shine? It's determined by the best absorption wavelength. So here would be like all the different wavelengths for this particular run. It measured wavelengths from 200 nanometers all the way to 300. And as we measured the sample, there's a very large absorbance at 217 nanometers. We call it the lambda max. It's the maximum absorption wavelength. So basically, the most amount of light is absorbed at this particular wavelength, and that would be the best place to make your measurements because you get the best readings. Now you could make measurements down over here, but it's just not quite as high of an absorption. And your goal is to get as close to 1 here and be in that range there. So you're looking for the peaks. Here's another example. Here's two different samples we're looking at here. So the best place to measure this substance would be somewhere in the 6 to 650 range here, because that's the maximum wavelengths will be, or the best absorption for a wavelength. And same for these ones. There's actually two different peaks, which sometimes occurs. You could do here or here, just depending on what maybe you're investigating. So experimentally, one of the first things you need to do before you actually even put your sample in is you have to use a blank solution. A blank solution is a solution that contains the same properties as the sample, except for the solid particle that's going to absorb the light. So for example, we're going to be doing a crystal violet lab this year. And the crystal violet is a substance that will actually absorb some light, and it's going to be an aqueous solution. So your blank for this one's actually going to be just water as a background. So you put a blank sample in here, and basically it's called a blank. It's just pure water in here, and you run this through. The blank is just meant to help kind of calibrate. Sometimes there can be some imperfections in your cuvette, which is this cube-shaped object here, rectangular prism. And the cuvette can have some imperfections, and sometimes the water has a few imperfections as well. And you want to do a blank solution just to kind of get a rough intensity measurement to kind of see what happens when you don't have any of your analyte, in this case like crystal violet, in there. So we put a blank in there. And I got a quick little video to kind of show you the difference. So here we technically have a blank right now, and we're going to be running some light through this blank here, and you're going to see a bunch of photons flying through here. So here they come. So here's the photons, and you can see that nothing is being absorbed here in the middle. And it's all going through. It's hitting the detector. It's hitting the detector on the right-hand side here. Then we're going to hit stop, and you can see that on average there's about 37, 38 photons per second hitting the detector. So your blank solution basically has a rough idea of how many photons hit this per second. Now we can do a sample, and your sample here, you can see that some of these purple dots are actually disappearing as they go through here. And notice, therefore, there should be less photons hitting here, and now there's about 23 photons per second hitting. Okay, let me pause this for a second. So basically, now that there's less photons hitting per second, the intensity went down because now the sample is absorbing some of those photons. So spectroscopy basically looks at what happens to the intensity of light as it goes through. Alright, up next. So I was talking about this intensity thing here. So we have a thing called transmittance. If you take the intensity, and the top intensity here, we're not actually going to do this, just so you know. If you take the intensity measured, so that last problem you kind of saw in the video, I think it was around like 23 photons per second. The original intensity here was about 38. Well, the fraction of that there, whatever that decimal number is, that's called the transmittance. And transmittance, if you graphed it versus concentration, it would give you a graph like this, where it's an inverse relationship. So as things get more concentrated, the percentage of light getting through there basically decreases. The intensity that you're going to measure decreases. Now, that's all fine and dandy. It turns out that transmittance, that non-linear relationship, is not a very good thing for us. So we are going to be using absorbance. And again, we're actually not even going to calculate this. We're just going to measure it. But absorbance is really just taking the transmittance and taking the negative log of it. And you get a graph like this. And notice how it's a nice linear relationship. So as concentration were to increase, and you would plot out the absorbances and then connect a line between all those, you get that black line there. You have a nice linear relationship between absorbance and concentration. So later on, we can measure some unknown absorbance, go to our graph here, and then we can go down and say, oh, this is the unknown concentration based on an absorbance we measured. That's what we'll be doing in upcoming labs. So factors that can determine the absorbance is cell path length and concentration. So the cell path length is basically how long your container is. Is it this wide, or is it this wide like you see on the screen here? And if you think about, the farther the light has to travel through the sample, the more light's going to be absorbed. So I got another video I'll show you here kind of demonstrating this as well. So here you're going to see different cell path lengths of 1, 2, 3, 4, 5 centimeters in length. Go back up. And when we hit start here, you'll see the light going through here, and you'll see some of the photons disappearing. Okay, so they're starting to disappear. We're detecting over here at about 190. The cell path length is now 2 centimeters wider. You can see that there's more and more photons. And basically, the wider our cell path length here, the longer light has to travel through the sample, the less particles, or more particles are going to be absorbed, and therefore less will come through here. So just kind of showing that the cell path length can determine how much light is absorbed. Up next, we have concentration. Concentration also can influence how much is absorbed, and this one's pretty simple. Basically, the more concentrated your solution is, the more light will be absorbed because there's more particles to absorb the light. So here's another quick example kind of demonstrating that. So in this demonstration, we got different concentration solutions here, and you can see that the green part here is going to get darker. And the darker or more concentrated it gets, you should see more and more purple photons getting absorbed here. So let's just kind of watch here. Okay, going to the next concentration, a little darker. You can see it seems like more and more purple photons are getting absorbed here. The detection's about 380. Let's see what the next one's at here. Come on, detector. Now it's about 350. And here's our most concentrated example in this little animation here. Now we're about 310 photons per second. So basically, the more concentrated this gets, the less photons are going to get through. All right. So that's your factors that can affect that. This actually goes into an equation now. It's called Beer's law. And it's one of the most common applications of spectrophotometry that's used in biology, physics, chemistry, geology, microbiology, etc. But we use it to determine the concentration of an analyte solution. And it's going to, in Beer's law, basically it's going to use linear relationships between absorbance and concentration, like we kind of showed earlier. And the equation for it is A equals ABC. So I like to say this equation is as easy as ABC. So big A here is absorbance. Oftentimes, just to kind of make sure I don't have two A's in my problem, I actually write the equation as ABS, which stands for absorbance, equals ABC. AP exam gives you this one, so get familiar with that one and just kind of know it. The little a here is going to be just a constant called the molar absorptivity constant. B is that cell path length we talked about. And what's nice about cell path length is that scientists, point to B here, scientists just use a 1 centimeter cell path length all the time. So that little cuvette thing we were talking about earlier, that rectangular prism that we'll put our samples into, it's nice and clear. These things are always set at a 1 centimeter path length. So that's going to be a constant as well. So basically those two things are constant. And then concentration is your other variable. So you can change concentration, and as we said earlier, if concentration goes up, absorbance should go up, and vice versa. So they have a nice linear, direct relationship. So in practice, what we're going to be doing is we'll take a series of standard solutions, and a standard solution is one in which we know the concentrations accurately. So I'll just make some numbers up here, but let's just say you make a concentration of 1 molar, 2 molar, 3 molar, 4 molar, and 5 molar. Those are called your standard solutions. You know what their concentrations are. Then the next thing is that we're going to measure the absorbance of those standard solutions, and then we're going to prepare a calibration curve. So again, this was 1 molar, 2 molar, 3, 4, 5 molar that we made perhaps. And then we're going to measure their absorbances, and their absorbances are this, 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 and this. So their absorbances went up, 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 and up. And then once you have them plotted, you can put a straight line on that thing there, a best fit line, if you will. And that best fit line there actually corresponds to our absorbance equation, A equals ABC, where absorbance here is the y-axis. On the x-axis, that's our concentration. And this component right here is the cell path length, and that's going to be the slope. And technically, if you have 0 concentration, you should have a 0 point right here. So your y-intercept here, it's just going to be 0, so we don't have that. So really, we have the slope of a line that intersects 0 that we can get from a Beer's law plot. And the slope here does correspond to those two things here, the cell path length and the molar absorptivity coefficient. And that's what we can use to basically find unknown concentrations in the future. So if I were to measure an absorbance right here, again, I could go over to my line here and say, okay, and go down, and I can find what the concentrations is. Or you actually plug into the equation, plug your absorbance in, and solve for the concentration that would be. So that is Beer's law and spectrophotometry. Come ready to be using this in some upcoming labs.